Deep within the cavernous concrete walls of a repair dry dock, a commercial vessel rests on massive wooden keel blocks. This towering steel hull is exposed to the open air for the first time in years of continuous service in the harshest environment, the sea. 3 men walk the length of this drying leviathan, each driven by different institutional priorities. The shipowner's superintendent calculates dock days against charter rates. The yard's coating manager tallies the blast pots and paint drums required. And the paint representative prepares to authorize the warranty on the entire application. Unlike a new building where every parameter is defined in a factory, this is a ship in active service. The true scope of the required repair remains a complete mystery until this specific walk begins. Together, they scour the steel to decide between a localized spot repair or a full, expensive abrasive blast. The decisions made during this 2-hour inspection will lock in the vessel's fuel efficiency and maintenance profile for the next 5 years. The team hunts for specific coating breakdown modes: well-dressed, mechanical scrapes, and osmotic blistering. This destructive phenomenon occurs when salt contaminants trapped beneath the paint draw in seawater through the coating, forming pressurized fluid-filled bubbles that lift the film from the steel. This assessment is quantified by a metric called average hull roughness, or AHR. While a new ship leaves the yard with an AHR of about 80 microns, 5 years of ocean service can push that figure past 200, creating massive hydrodynamic drag. This microscopic profile tracks surface roughness. A 25-micron increase imposes a 1% fuel penalty. For a typical container ship, that wastes $328,000 yearly. With severe biological fouling, the penalty hits 40%, costing tens of millions and thousands of tons of excess CO2. Maintaining a perfectly smooth underwater hull is a foundational requirement for commercial survival. Today, it serves as a primary instrument for meeting international decarbonization obligations under the IMO's Carbon Intensity Indicator rating regime. Once the scope is defined, the dock becomes an environment where dozens of workers and tons of abrasive grit converge on the hull. Blasting teams strip damaged sections down to near white metal, ensuring the surface is free of all mill-scale, rust, and foreign matter. Before the spray guns are deployed, workers manually apply a stripe coat. They use brushes to push paint onto weld seams and sharp edges, where sprayed paint would naturally draw thin under surface tension. Without this brush-applied layer, these edges would be the first to fail at sea. Operators then apply primary top coats using high-pressure airless spray. They choose between self-polishing copolymers, which chemically release biocides to co-growth, or silicone-based foul release coatings that create a non-stick surface so smooth that marine organisms slide off at cruising speed. This advanced chemistry is entirely at the mercy of the weather. Application requires relative humidity to be below 85% and the steel temperature to remain at least 3 degrees above the dew point to prevent condensation. If applied in high humidity, epoxy coatings can develop amine blush, an invisible waxy film. This blush destroys the adhesion of any subsequent layer, condemning a multi-million-dollar paint job to premature failure. Moving from the exterior into the ship's belly, we enter the dedicated seawater ballast tanks. These compartments undergo a punishing wet-dry salt cycle as they are filled for stability and then emptied, making this the most corrosive shipboard environment. To prevent the sudden structural failure of tankers and bulk carriers, these spaces are governed by the strict IMO PSPC standard. This regulation mandates abrasive blasting to a white metal finish and the application of specialized multi-coat epoxy systems designed for a 15-year life. Renewing these coatings involve extreme confined space hazards. Painters must navigate jagged internal geometries, maneuver heavy blast hoses through tight 700mm spaces, all under continuous atmospheric monitoring. Inspectors enforce a rigid 90-10 rule for paint thickness. 90% of all readings must meet the nominal target, and no single reading in the remainder may fall below 90% of that value. Achieving this statistical precision by hand in a dark, cramped steel box is one of the most demanding trades in ship repair. Because no coating is microscopically perfect, every vessel carries a second line of defense. This is cathodic protection, an electrochemical system that activates the moment the paint film is scratched or damaged. On large vessels, passive sacrificial anodes are supplemented by impressed current cathodic protection. Instead of consuming metal blocks, this system uses a transformer rectifier to convert ship power into a low-voltage DC current, which is discharged through titanium anodes to protect the hull. Embedded reference electrodes constantly measure the electrochemical potential between the hull and the seawater. The controller uses this data to automatically trim the current output in real time, holding the hull within a precise protective window. However, this system creates a mechanical danger. The main propeller shaft is insulated from the hull by a thin film of lubricating oil. Without a path to ground, the protective current will arc across that oil film to reach the ship's structure. Without a functioning $2 shaft earthing brush to provide that ground, this microscopic sparking will progressively destroy the engine's white metal bearings. A total main engine failure at sea can often be traced back to this single worn-out brush. With the hull restored and the systems calibrated, the dock floor is cleared. Millions of gallons of ocean water rush through the sluice gates, lifting the vessel back into her natural element. Refloating is a high-risk engineering procedure. Internal ballast must be adjusted in real time as the water rises, so that the vessel's weight distribution matches its emerging buoyancy. An uneven lift off the keel blocks can impose bending moments severe enough to crack welds or even fracture the keel. Every ton of water must be accounted for to ensure the hull girder remains stable. As the vessel clears the dock gates, her perfectly restored coatings and calibrated electrochemistry must protect her against the sea for the next 5 years of service. While this vessel returns to its routine trade, other ships enter these docks for radical transformations. Join us next time as we look at ships that are lengthened, widened, and physically cut in half to be rebuilt for entirely new missions.